just picking up where we have left off in the case of asymptotes, and we have been looking into domain and vertical asymptotes, and more recently horizontal as well as slant asymptotes. And again, just with the rules of thumb, if you have a rational function where you have n to represent the degree of the numerator, m to represent the degree of the denominator, if n is less than m, that is, if the degree of the numerator is less than that of the denominator, okay, there will be a horizontal asymptote y is equal to 0. And if the degrees are the same, there's going to be a horizontal asymptote which will not be the x-axis, like y is equal to 0, but instead you will have y equal to the constant that comes from reducing the ratio of what we have in the highest degree terms. And if we have that the numerator degree is greater than the degree of the denominator by a power of 1, there's going to be a slant asymptote, which we have like y is equal to alpha x plus beta. And again, that's just another variation of what we have with the slope-intercept form of a linear equation. And if the difference in degrees is such that n is higher than m by more than 1, there will not be a horizontal or slant asymptote. And just looking for the domain and the asymptotes, and we have in reference to section 2.5, okay, say we have a rational function f of x is equal to 4x minus 9 all over x squared minus 9. And if we look for the domain, okay, so we have again, we have the restriction that the denominator cannot be 0 in value. Okay, so we have the x squared minus 9 cannot be equal to 0. Okay, so we have the denominator is going to be a difference of squares. And so we have,
okay.
All right, so we got for this one, sorry.
The difference of squares. Check it out.
Sorry. Okay, so you have the quantity of x plus 3 times the quantity of x minus 3 cannot be equal to 0. Okay, and so for the factors here, okay, we have the x plus 3 cannot be 0. And we have that x minus 3 cannot be 0. Okay. Okay, so if x plus 3 cannot be 0, okay, we have that x cannot be negative 3. And if x minus 3 cannot be 0, we have the x cannot be equal to 3. Okay. And so we're going to have for the domain, okay, so you have with the two exclusions from the domain, we have that negative 3 is the smaller exclusion, so the domain at the lower end, you're going to have those values of x less than negative 3. And we also have, after bypassing negative 3, okay, you have the next set of values. You have those values of x such that negative 3 is less than x is less than 3. And for the rest of the domain, you have those values of x which will be greater than 3. All right. And for what we have in the case of the ratio, okay, now f of x is already in simplest form. There is no common factor that exists between the numerator and denominator, okay, where we can reduce this any further. Okay, so we have that f of x is already simplified. And so that means that what we have here with negative and positive 3, okay, those are going to be the vertical asymptotes, since their factors would not cancel. Okay, so you have two vertical asymptotes, and to see if we have any other asymptotes in the mix. All right, so looking at what we have in the degree comparisons. Okay, so you have from 4x minus 9, okay, the variable term, the only one that we have at the top is 4x, and the x is to the first power. And in the denominator, okay, we have from x squared. This signals that the degree of the denominator, okay, is going to be at 2. And so for what we have in this case, we have n at 1, m at 2. And we're going to have that n is less than m. And with the rules of thumb, okay, so if n is less than m, there's going to be a horizontal asymptote, y is equal to 0. Now, for what we have in terms of the graphing, okay, so we have three asymptotes: two vertical with x equal to -3, x equal to +3, and a horizontal asymptote, y is equal to 0. And for what we have in the case of 4x minus 9 all over x squared minus 9, and again, so we have two vertical asymptotes, okay, where we have x equal to -3, x equal to +3, and we have the horizontal asymptote, y is equal to 0. And again, for what we have in the graph, okay, this is what we have with our function f of x at 4x minus 9 all over x squared minus 9. And just to restate, now in graphing, vertical asymptotes are always going to be off limits. But if you notice, okay, for the middle section, you have the graph of f of x, that portion between the vertical asymptotes happens to intersect and even cross, okay, the horizontal asymptotes. You have contact with y is equal to 0. And just a reminder, now a rational function can come into contact with horizontal and slant asymptotes under extenuating circumstances, but never will a rational function come into contact with any vertical asymptote. So I just wanted to reaffirm this. All right, now for what we have in the case of the next item, and we have with number 60, okay, and much of the process, okay, is going to be maintained. For we are going to have a difference of squares again in the denominator. And in number 60, okay, we have that y is equal to f of x. And that is equal to 5x minus 8. All over x squared minus 4. And if we look for the domain, so we have a difference of squares with x squared minus 4. And for the rational function to be defined, again, the denominator cannot be equal to 0. And so we have here with the factors, neither of which can be 0. So for x plus 2, if this cannot be 0, okay, we have that x cannot be negative 2. If x minus 2 cannot be 0, okay, well, we have that x cannot be equal to 2. So we have two exclusions from the domain, and like what we have in number 59, okay, we had the exclusions to be additive inverses. And for what we have for the smallest values, okay, we're looking at those values of x less than negative 2, along with those values of x such that negative 2 is less than x is less than 2. And for the rest, we have those values of x which will be greater than 2. And again, okay, we have for f of x, this is already simplified. And you can change the layout, but it will be in the form of expressing x squared minus 4 in factored form. And neither x plus 2 nor x minus 2 will be factors that will be common to the numerator. Okay, so those factors would remain, and so we have both exclusions from the domain to be the vertical asymptotes. And once again, looking at the comparison of degrees between the numerator and denominator. So you're going to have, once again, another bit of history to repeat. Once again, we have in the numerator, we have from 5x. X is a first degree, so we have that n is equal to 1. And the variable term in the denominator is x squared, so we have that m is equal to 2. And we have another case whereupon n is less than m. And we will have, once again, a horizontal asymptote whereupon we have that y is equal to 0. Okay, so again we have three asymptotes, two vertical, one horizontal. And for what we have, again visually, it's kind of like the graph we had in number 59. Okay, so you have this time you had the vertical asymptotes, x equal to negative 2, x equal to positive 2. And once again, the x-axis, or y equals 0, is going to be the horizontal asymptote. And again, this function f of x, we have, again, split up into three sections. And again, we have the middle section to cross the horizontal asymptote. But again, this graph, or any rational function graph, is not going to come into contact with any vertical asymptote. All right, now, so we have for 59 and 60, okay, we had the denominator to consist of, okay, the horizontal asymptote, or the denominator to consist of differences, or a difference of squares. And we also had the numerator to be 1 degree less than the denominator. Now for what we have in the case of the next item, okay, we have not with 60 but number 70. And this time we have our function y is equal to g of x. And that is equal to x minus 3. And we have this all over x minus 1. And to keep g of x defined, okay, there is only one restriction, and that this time we have with the denominator x minus 1, which cannot be 0. And so if x minus 1 cannot be 0, okay, well, we have that x cannot be equal to 1. So you have with the domain, then we have two halves. First half is going to be those values of x, which will be less than 1. And the upper half, we have those values of x greater than 1. And just like the functions in numbers 59 and 60, okay, g of x is already in simplest form. So this means that this exclusion from the domain will form the only vertical asymptote with the vertical asymptote at x is equal to 1. And for what we have in the determination of whether we have any other asymptote, and in both the numerator and denominator, okay, we have the variable term to be x. And x is of first degree, so n is equal to 1. And we have that m is equal to 1. And so we have both n and m have identical values. So we have that n is equal to m. And this time we're going to have a horizontal asymptote, whereupon we're going to have that y is equal to the constant that is formed upon taking the higher or highest degree terms from the numerator and denominator and dividing out. Okay, so from the numerator we have x, and the denominator we have likewise, and x over x is equal to 1. And for the graph on this one, okay, again, we don't have drawn according to scale. I just mentioned, okay, so this time we have vertical asymptote at x is equal to 1, and hovering above the x-axis, okay, we have the horizontal asymptote y is equal to 1, and we have for g of x, okay, this is broken up into two separate sections. All right, and now for what we have in the case of rational functions. Okay, we now have in the case of number 72, and once more changing up the variables. Okay, so I've gone from f of x to g of x, and in 72 I have this time representing y. Okay, we have h of x, and in 72 we have that h of x is equal to 2x minus 4 all over x plus 3 and for what we have in the case of the determination of the domain. Okay, so again, we had the restriction that x plus 3 cannot be 0. So we have that x cannot be negative 3. for the domain, okay, so we have for the lower half, okay, we have those values of x which will be less than -3. Along with those values of x which will be greater than -3. And so we have with h of x. Again, so this is already simplified. And just a reminder, if I had the numerator to factor out and one of the factors be x plus 3 would completely go out. And instead of having a vertical asymptote, x equals -3 would be a hole in the graph. But for what we have instead, okay, x equals -3, again, is going to be the only vertical asymptote. And in finding any other asymptote, again, this comes down to the degree comparison between what we have in the numerator and the denominator. Okay, so we have in the numerator, okay, we had the variable term to be at 2x, and we have the x is going to be a first order. And a bit of history repeating, we have the same thing in the denominator, okay, where we have x as a variable term, also a first order. So we have that n is equal to 1, and we have the m is equal to 1, and we have the n is equal to m. And from this, okay, we're going to have a horizontal asymptote, okay, which you're going to have upon taking the ratio of the higher or highest order terms in the numerator and denominator. Okay, so in this case, we had that y is equal to 2x over x, and that is equal to 2. Okay, so again, just like g of x, okay, we have two asymptotes, one vertical and the other horizontal. And we have for the display case, so for the graph f of x, okay, you have this portion, okay, or this function, okay, to be broken up into two sections. And again, we have much of the graph, okay, have running tangent to the horizontal asymptote, again, which we have at y is equal to 2, and also running tangent and never coming into contact with the vertical asymptote, which we have at x is equal to -3. All right. And okay, so far we've had a mix of vertical and horizontal asymptotes. Now, for what we have in the case of the next item, and we have with number 86, and we have for this one, okay, so we have that for 86, so we had the variable, okay, so you have in terms of u of x, and that is set equal to -3x squared all over x squared plus 1 And for what we have in the case of this ratio, so we got -3x squared over x squared plus 1. Okay, I'm just going to mention now, again, we have the restriction, if there is to be any, this would be where the denominator is equal to 0. And if we have any exclusions from the domain, so again, x squared plus 1 cannot be 0. And in terms of real terms and integer coefficients, okay, now we cannot factor a sum of squares. Now a difference of squares, we can, like x plus 1, x minus 1. But for x squared plus 1, okay, we just have to go through a different pathway. So if I were to move the 1 over, we have that x squared cannot be equal to -1. And borrowing from the page, okay, where we have utilizing the square root property of equality, but where instead of equal, I have not equal. So if I go from x squared to x, and we have -1 to go to plus or minus its square root values. And so we have the x cannot be plus or minus the square root of -1. And so we have x cannot be plus or minus I. Okay, and from what we have here, notice that we do not have any real terms excluded. So that means a couple of things here. Okay, first of all, if there are no real terms excluded, okay, now the domain is going to be the set of all real numbers. And to just formally stating for the domain, okay, the interval notation for all real numbers, you have anything between negative and positive infinity. Okay, so that's saying you could plug in 0 for x, as well as any positive, negative value, and you can plug in anything, and whatever you have for x squared plus 1 is not going to result in a 0. The only way it could result in 0 is if you took it from the complex number system, which we're not dealing with anymore. Okay, and so you have no real terms excluded. So you have the domain is going to be the set of all real numbers, and since we have no real terms excluded, that means that there's going to be no vertical asymptote. Again, for any possible vertical asymptotes, there must be some exclusion from the domain. Okay, so you don't have a vertical asymptote. And now to see if we have any asymptote period. Again, this is going to rest upon how the degrees compare between the numerator and denominator. Okay, so we have in the numerator, okay, we have 3x squared. So we have the n is equal to 2, and we have in the denominator, we have the m is equal to 2. So we have n and m with identical values. So we have the n is equal to m. And so we're going to have a horizontal asymptote where y is going to be the constant upon taking the ratio of the higher or highest degree terms from the numerator and denominator. Okay, so you have negative 3x squared from the top, and from the denominator, okay, we have x squared, and negative 3x squared divided by x squared will come out to negative 3. So for this rational function, okay, there's going to be only one asymptote, and it's going to be that which is going to run horizontally in the form of y is equal to negative 3. again, for this graph, okay, you're going to have u of x. Okay, if you were to graph, you would have situated, except for the origin. Okay, you have almost the entire graph. Well, actually, the entire rest of the graph is going to be situated below the x-axis, and we have at the far end, you're going to have running tangent to the horizontal asymptote, which we have at y is equal to -3. And we have both halves of the graph are going to be mirroring each other, and the formation of it is going to be something about like what they call a normal distribution curve or a bell curve. So that'll be the formation of what we have for this particular rational function, again, which we have with u of x is equal to -3x squared all over x squared plus 1. All right. And now, so this is, I think, our first case of where we have an asymptote, but no vertical asymptote in the mix. Now, for what we have in the case of number 90, okay, this time we have going back to f of x. And for this rational function, okay, so you have y is equal to f of x, and that is equal to 4x to the fourth. And that is all over x squared plus 8. Okay, and this is a distinct problem we're going into, but there are some filaments of what we have with number 86 that will be carried over for what we have in the denominator. Again, we're trying to exclude those values that cause the denominator to be 0. And if you notice, we have, like, in a sense, we have a sum of squares, but we have 8 is not exactly a perfect square, but like number 86, we're going to isolate the x squared, so I can move the 8 over by subtracting and going from x squared to x. So I have a reapplication of the square root property of equality, except where I have the not equal instead. Okay, so you have for x, if we're saying that x squared cannot be -8, we are in effect saying that x cannot be equal to plus or minus the square root of -8 and so you have x cannot be plus or minus the square root of 8i, and you need not lower this, but in reduced radical terms, you have x cannot be plus or minus 2 times the square root of 2 times I. But again, so you have no real values excluded. And once again, you're going to have for the domain, okay, we're going to have the set of all real numbers. And since there are no real values excluded, okay, there are no exclusions from the domain where we could possibly have any vertical asymptotes. And to see if we have any asymptotes, period. Okay, so looking at the variable terms in the numerator and denominator. Again, we have 4x to the fourth all over x squared plus 8. Again, we have in the numerator. Okay, we have from x to the fourth, we have the n is equal to 4, and from the denominator, we have that m is equal to 2. And out of our possibilities now, we have that n is greater than m it's greater than m by 2. Or in this case, for our 4 cases, we had the last one to apply. And so out of the 4 possibilities regarding horizontal and slant asymptotes, if n is greater than m by more than 1, you're not going to have either a horizontal or a slant asymptote. Okay, so there is no vertical asymptote to begin with. There's not going to be any horizontal or slant asymptote. Okay, so the graph of this rational function is not going to be constrained by any asymptotes. And just for the appearance, kind of a rough appearance of this graph. Again, once you get away from the origin, now when you're close to the origin, it might seem to suggest that you might have y is equal to 0 is going to be a horizontal asymptote, but as you get farther out to the right and to the left, you don't have anything that's like coming close to bordering the horizontal asymptote. What might otherwise be the horizontal asymptote with the x-axis, and also you have in terms of vertical asymptotes, there are none of those because you have like the dynamic of the graph is moving upward, and it's also moving continuously both to the left and also to the right. Okay, so this is a case of a rational function that is not constrained by any asymptotes. All right, and we'll be looking at how the behavior of the graph of rational function can tie in with what we have looked at earlier when we had in behavior, zeros, multiplicities, and also where the graph crosses and touches the x-axis. And okay, but we're going to look over for the next portion, and we have just in the remaining parts of what we have with chapter 2. Okay, we have with inequalities, and the first half or the first portion of what we have with inequalities would be those that we have concerning polynomials. Okay, so for this item, in the case of polynomial inequalities, okay, and again, inequalities are your statements like less than, greater than, less than or equal to, as well as greater than or equal to. And this will kind of get us started off. Okay, now let's say that if you have an equation along with inequalities, okay, say we're looking at determining the values of x, okay, for the following. And we're just going to have comparison to 0, okay? And so we have just working around what we have with x squared minus 4. So you have x squared minus 4 is equal to 0. And say we have x squared minus 4 is less than 0. And say we have x squared minus 4 is less than or equal to 0. and then changing the direction. Okay, so we have x squared minus 4 is greater than 0, along with x squared minus 4 is greater than or equal to 0. Okay, so we have for the first part, okay, so you have just the equation x squared minus 4 is equal to 0. Okay, and we can get to that solution rather quickly since we have a quadratic function already set up in standard form, and where we can solve by either the square root property of equality or by the zero product property. Now, tell you what, since we have x squared minus 4 on the left hand side, I'm just going to write this in the factored form. Okay, so you have x plus 2 times the quantity of x minus 2 is equal to 0. And if that is true, okay, then one of these factors has to be equal to 0. And if we have the x plus 2 is equal to 0, we're going to have the x is equal to negative 2 and for the other, okay, we have the x is equal to positive 2. Okay, now in terms of laying the groundwork, okay, in terms of solving for these inequalities, okay, notice we have that which has been compared to 0 throughout. So we had x squared minus 4 and to solve for the inequalities, okay, we can go ahead and attain or work with the zeros. So yeah, with the zeros, again, we have solving x squared minus 4 is equal to 0, and so we had additive inverses. Okay, and so we have with negative and positive 2. And just creating a backdrop, okay, to solving for these inequalities. Okay, I can set up a table. First of all, okay, so we have so yeah, an interval. And I'm going to work a bit about the real number system. Okay, so if you were to look at what we have for the zeros, so you have negative 2 and positive 2. And I'm going to set up the table almost like if you had negative 2 and positive 2 as exclusions from the domain. So what I'm going to do here, like the first interval section, okay, have, say, like those values of x that will be less than negative 2. And then bypassing negative 2, and we'll have those values greater than negative 2 and less than 2. And we have for the rest, okay, we have those values of x greater than 2. Okay, so we have, in this case, so we have 3 distinct interval sections. And what I'm going to do here is I'm going to separate these and just kind of partition out into separate rows and columns. Okay. And we have like separate rows here. So underneath the heading of interval, have like test value for the input. Now the input variable we have with x. And I'm going to determine the output for each of the selected input values. again, so you have with our function, we have f of x is equal to x squared minus 4 and also have looking at the sine of f of x okay. So first of all, okay, I can choose like arbitrary values from each of the sets. Okay, and say we have like a test value x, like, okay, so for the first, okay, we have the interval description is that we're looking at making reference to those values of x less than -2. So I can select a value that is less than -2. So I could go with like -10, -100. And usually I like to keep the absolute value of what I select is pretty much as low as possible. And okay, you can go with -3. And if you chose -4, -5, it still qualifies as a selected test value. Now for what I have for those values of x such that -2 is less than x is less than 2, if I want to go with an integer, I could choose -1, 0, or 1. And I like to go with 0 when I can. And then anything greater than 2 or the last, okay, I can go with +3, that would qualify, and I'll just go with 4 on this one. Okay, as long as what you select belongs as an element that pertains to what we have in the interval described, okay, you're good to go. Okay, so for f of x equals x squared minus 4, so you're looking at f of -3. As well as f of 0 and also f of 4. Okay, so these are the selected x values. Okay, we're just going to work with. So for f of -3, so we have x squared minus 4 so you have -3 squared minus 4. Now -3 squared is going to be a +9. 9 minus 4, okay, this will come out to a +5. Now for f of 0, okay, so we're looking at 0 squared minus 4. 0 squared is 0. And 0 minus 4, okay, this will come out to a -4. Now for f of 4, okay, so plugging in, so you have x squared becomes 4 squared and 4 squared is 16. Again, we have minus 4 to follow. And 16 minus 4 comes out to +12. Okay. Now for what we have regarding the sign of f of x, so anything less than -2 we select for the input. The output is going to be positive. So with f of x as the output, if the output is positive, that means that f of x is greater than 0. If on the other hand, let's say for the next, anything I select greater than -2 but less than +2 for x, okay, the output is going to be negative, just like 0 for the input leads to a -4 for the output. So here I'm going to have the f of x is less than 0. And going back, okay, so if I select anything greater than 2 for the input, the output is going to lead to a positive value. In this case, all right, so we have, once again, the f of x is going to be greater than 0. All right, now looking at what we have for the inequalities. Okay, so for the first problem, I had -2 and +2 whenever the function is equal to 0. Okay, now for x squared minus 4 is equal to 0. Okay, note that f of x is equal to x squared minus 4. And using these results in the bottom row to signal, okay, just what's going to be in the solution. So we have x squared minus 4 is less than 0. And again, f of x is defined by x squared minus 4. So we're looking at where we have f of x is less than 0. And for the solution, okay, so we'll be looking at where f of x is less than 0. So this is occurring in the middle section. And for those values of x, they'll be found in the top row within the same column. Okay, so for those values of x, it'll be those values of x for which negative 2 is less than x is less than 2. Now for x squared minus 4 is less than or equal to 0. So this would be like saying that f of x is less than or equal to 0. Okay, now we have a different inequality, but we have going in the same direction. Less than or equal to 0 is in the same direction as f of x is less than 0. So we are still involving the limit values with negative and positive 2. Okay. Now with the equal sign, okay, that means we can potentially use grouping symbols other than just parentheses. And guess what? You got, now when we had just less than 0, you had automatically parentheses around negative and positive 2. But with the equal sign, again, we had negative and positive 2 to create the x squared minus 4 is equal to 0 portion. And since negative and positive 2 create the equal portion and the inequality includes the equal sign, that means that these values will be included in the solution. Question? So we got here.
I'm sorry, I didn't mean to click that.
Okay, that's all right. Okay, so since we have negative and positive 2 included, that means that we're going to have brackets to go around those values. Okay, and for what we have in the case of the next statement, so I'll just bring this over. And now we have x squared minus 4 is greater than 0. And for what we have in the case of the solution, okay, so again, x squared minus 4 is greater than 0. So you have for f of x is greater than 0. Guess what? We had 3 interval sections, and there was only one where f of x was less than 0. So I had this rather short solution set. But now for the greater than, as well as the greater than or equal to 0, okay, the solution set is going to be in more expanded form. For we have for f of x is greater than 0, we have referencing the first and the last subinterval sections. And so for greater than 0, automatically, okay, we have at the lower end, we have those values of x less than negative 2. And we have at the upper end, we have those values of x which will be greater than 2. And finally, we have with the remaining solution set, so we have with x squared minus 4 is greater than or equal to 0. Which we have the equivalent of saying that f of x is greater than or equal to 0. Okay, so greater than or equal to 0. Again, you have the same direction as f of x is greater than 0. So we're still looking at working around the limit values from f of x is greater than 0. And in terms of the grouping symbols, again, infinities are boundless, so we maintain the use of parentheses. And again, just like earlier, okay, we have negative and positive 2 for x to create the equal to 0 part. And since we now have those values again to be part of the solution, thanks to the equal sign included, we're going to have the reapplication of brackets. And so that will be the interval solution of what we have for this last inequality. All right, now some things we have here, and there's going to be a bit of transitioning, and we have with polynomial inequalities, and we have in section 2.6. Then we have in the case of, say, for item number 17, okay, now you're going to have for the centerpiece of this, okay, you're going to have a function whereupon we have that f of x is equal to negative x squared plus x plus 12. Okay, now this problem is going to have like 5 parts once again. And now for f of x, you have negative x squared plus x plus 12. Now the first part, you're looking at the values of x for which this polynomial is equal to 0. Okay, and so if I set things up here, so we have negative x squared plus x plus 12 is equal to 0. And okay, and what I want to do here, just to make this factor friendly as much as possible, and I want the leading term to be a positive x squared, so I could just multiply the equation or divide the equation by -1, or in other words, make what was negative positive and vice versa. Okay, so we have x squared minus x minus 12 is equal to 0. And so putting what I have in the adjusted quadratic equation in factored terms. Okay, so from x squared, this time I have x and x, and factors of negative 12 whose sum or difference will be -1. Okay, so I have more weight given to the subtracting than to the addition. And we have with the zero product property. Okay, so itemizing the factors and setting equal to 0. So from x minus 4 equal to 0. So we have the x is equal to 4. And from x plus 3 is equal to 0, and we have the x is equal to -3, right? And so in setting things up, kind of like applying what we have for the comparison to 0 inequalities. Okay, so again, we have our given function, f of x, is equal to negative x squared plus x plus 12. Now, in the case of the zeros, okay, so you got the zeros with 4 and -3, and it doesn't matter what order you place them, but if I'm looking at setting up a table like earlier, I'm just going to arrange these in increasing order. Okay, so this is our function, these are the zeros, and setting up a table like what we had just moments ago. and to more or less span the real number system. Okay, so starting from negative infinity, I have approaching the lesser of the two zeros in this case, which is going to be -3. I have bypassing -3, and I have approaching but not including 4. And then we have for the rest of the case, I have those values of x, whereupon we have the x is greater than 4. Okay, so just establishing the column headings. And again, just testing out each of the interval sections. Okay, so again, I'll be doing a bit of probing. Okay, so you have like your test value x. Again, applying the inputs, okay, to the given or polynomial function case, you have -x squared plus x plus 12, and again we have the sign of f of x. Okay, so for test values that we can apply, so we have for the first section, okay, so for anything that we have to be less than -3, okay, we can go with, we'll say -4. And anything between -3 and 4, okay, 0 is a possible choice. Anything greater than 4, we'll just go with 5. All right, now for our function f of x. Okay, so I'm looking at, once again, f of -4, f of 0, as well as f of 5. Okay, so we got for -x squared plus x plus 12. Okay, and again, so substituting -4 for x, so I'm looking at the opposite sign of the square of -4. We have plus -4 plus 12. Okay, now the square of -4 is going to be positive 16, but I'm still taking the opposite sign of that number's square. So while -4 squared is 16, the negative of x squared is still going to translate to -16. Then I have -4, followed by the addition of 12. And -16 minus 4 is -20. -20 plus 12 comes out to -8. Now for f of 0, okay, so I'm looking at for inputting, okay, so I have like the negative of 0 squared plus 0 plus 12. Again, the first two terms automatically negligible. And so f of 0, okay, this will come out to positive 12. And for f of 5, so I have the negative on what's going to be the square of 5. Plus x, I have plus 5. plus 12. So 5 squared is 25. But now I'm taking the opposite sign of 25. So we have negative 25. If I add 5, so negative 25 plus 5 is negative 20. In turn, we have negative 20 plus 12, which is going to come out to negative 8. And so for what we have in this one case, so any value of x selected that is less than negative 3 is going to lead to a negative output, such as negative 8. So here we have the f of x is less than 0. Anything greater than negative 3 but less than 4 selected for x, like 0 being an example, is going to lead to a positive output, just like 0 leading to positive 12. So we have the f of x is greater than 0, and anything greater than 4 is going to lead to a negative output. So we're going to have that f of x is less than 0. Okay. And now, so just kind of winding things back up. Okay, so we have for part A, again we had, this is asking for the solution to x whenever negative x squared plus x plus 12 is equal to 0. See, again, it kind of comes back to this part. Yeah, with the solution values. Okay, so you have x equal to negative 3 and 4 only. Okay, now for the inequalities are going to come in. Okay, we have the inequalities expressed in the form of comparisons to 0. Okay, so where we have negative x squared plus x plus 12 is less than 0. Okay, so again, your f of x, you have negative x squared plus x plus 12, and where that is less than 0, we can reference where f of x is less than 0. And from the table, where f of x is less than 0, we have with the first and last subinterval sections. And since there's no equal sign, again, we have just the use of parentheses as the exclusive grouping symbols. Okay, so you have those values of x less than negative 3, along with those values of x which will be greater than 4. And for C, again, where we have negative x squared plus x plus 12 is less than or equal to 0. So we have the f of x is less than or equal to 0. Again, same direction as f of x is less than 0. So I'm involving the same numbers. Okay. Again, infinities are boundless. And again, we had the negative 3 and 4 to create the equal to 0 part. And since the segment has the equal sign, this signals that negative 3 and 4 are part of the solution, and so they will be enclosed in the brackets. And going the other way, okay, so for negative x squared plus x plus 12 is greater than 0. So we're looking at where f of x is greater than 0. And this will be in this middle section, and the exclusive values will be those values of x whereupon -3 is less than x is less than 4. And guess what? We won't have those, okay, where -3 and 4 are excluded due to the lack of the equal sign. We will have with part E, with the inclusion of the equal sign, where we have -x squared plus x plus 12 is greater than or equal to 0. We're going to have -3 and 4 to be bracketed. Okay, so for polynomial inequalities, if you have the equal to 0 parts and your values create the situation where the polynomial is equal to 0, you're going to have those values to be bracketed, just like what was the case with -3 and 4 with the less than or equal to 0 and the greater than or equal to inequalities. Now, in looking at, let's say, for an inequality that is not yet expressed in comparison to 0 terms, and we'll say that we have for number 26, okay, just taking this as the case. Say if you're looking at solving for one particular inequality, okay, and say we have for the variable d, so you have d squared is greater than or equal to 6d. Okay, so you got d squared is greater than or equal to 6d. And I'm just going to mention, okay, so you got, just kind of setting things up. Now I can write this as a comparison to 0 inequality if I shift or move over the 6d to the left-hand side. So for d squared minus 6d is greater than or equal to 0. And if I were to put this in functional terms, this is like f of d is greater than or equal to 0. And I can determine, okay, what the zeros will be. And say if I have, instead of the inequality, if I locate the zeros I'll be using in the table. So if I have like d squared is equal to 6d, now rewrite this as a quadratic equation in standard form. So you got d squared minus 6d is equal to 0, and here I can factor you got d times, okay, the quantity of d minus 6 is equal to 0. So from the first factor d, okay, I have automatically 1 0 at 0. And with the other factor at d minus 6, if d minus 6 is equal to 0, I want to have that d is equal to 6. Okay, so just taking what we have, say just being able to use tabular setup. Again, so you have d squared minus 6d greater than or equal to 0. We can write this as f of d is greater than or equal to 0. So I have, say, like from this, you can say that f of d is equal to d squared minus 6 times d and this function is going to have a couple of zeros, one of which we have at 0 and the other at 6. And just setting the stage, okay, for solving this inequality. Okay, so just setting things up in interval terms. So you have two exclusions from the domain. And we have for the smallest set, you will have those values of d less than 0. We have those values of d between but not including 0 and 6. And we have at the highest end, we have those values of d which will be greater than 6. Okay, so looking at separating, okay, so just as we had tested value x to start things off, okay, now we're going to have tested value for the input letter. So you have the tested value d. So here we have to select a value that is less than 0. I'll say -1. Anything between 0 and 6, I'll just go with the number 2. Anything higher than 6, I can select the number 7. And we have for the next row, okay, so you have f of d. Okay, so you have d squared minus 6d. So with the tested values, with the inputs, so I'm looking for f of -1, as well as f of 2, along with f of 7. Okay, so just taking what we have for f of -1, so I have the square of -1 minus 6 times -1, -1 squared. So the square of -1 comes out to 1. -6 times -1 comes out to +6. And 1 plus 6, okay, we have a +7. Now for f of 2, okay, so d squared translates to 2 squared minus 6 times d, okay, translates to -6 times 2. 2 squared is 4. -6 times 2 is -12. And 4 minus 12 comes out to -8. And for f of 7, okay, so with 7 as the input, so I'm looking at 7 squared minus 6 times 7. 7 squared is 49. -6 times 7 is -42. And 49 minus 42, okay, this also comes out to +7. And for the sign of f of d, okay, so for the sign of f of d, okay, for any negative input, the output is going to be positive. And for the next, okay, the output is going to be negative, whereupon I have the f of d is less than 0, and then we have for the last, we have a positive output. Okay, whereupon we have that f of d is greater than 0. And since there was only one inequality to solve for, and this is where we had d squared was greater than or equal to 6d, again, that had become, and the rewrite, a comparison to 0 inequality. And again, just leading up to where we have f of d is greater than or equal to 0. So for the solution of this inequality, okay, the solution set would be those values of x that form the greater than or equal to 0 portion. Okay, so so you have in the solution, okay, so we got for f of d is greater than or equal to 0. It's the same direction as f of d is greater than 0. So we're involving, okay, the values negative infinity and 0, and the greater than 0 part we have with 6 and infinity. And in terms of enclosing, again, infinities are boundless. Okay, so we still have the use of parentheses around these. And with the inclusion of the equal to 0, okay, again, d equals 0, d equals 6 will cause the existence of d squared minus 6d to be equal to 0. And so we have for the rest, okay, we have 0 and 6, and we have the containment, okay, to be brackets. So you have a bracket around 0 and a bracket around 6. And so this will be the interval solution for what we have concerning this particular inequality. And tell you what, just looking at solving inequalities, okay, just for these portions, still working with polynomial inequalities. Let's see what we get for number 29, where we have looking at solving for m, whereupon we have m squared is less than 49. Okay. And also in the case of number 33, and this is going to be laid out as a comparison to 0 inequality and the function we have expressed in factored form. So we can get to the zeros rather quickly. Okay, so we have the quantity of x plus 4 times that of x minus 1. Then we have times that of x minus 3. Is greater than or equal to 0. Okay, so looking at what we have in numbers 29 and 33. Okay, so if I were to rewrite m squared is less than 49 in terms of a comparison to 0 inequality, okay, and just go ahead and get to the zeros of m. Okay, so again we have m squared is less than 49. And rewriting in comparison to 0 terms, okay, so I have m squared minus 49 is less than 0. And so just making a bit of an advanced reference. Okay, so let's say I have the function is f of m, which is less than 0. And looking at what we have for m squared and 49. Okay, so if I identify the zeros to work around, so if I have that m squared is equal to 49, and again you can use the square root property of equality to get to the zeros, but again I'll just rewrite this in standard quadratic equation form. Okay, so we have for m squared minus 49, okay, so you have a difference of squares, okay, and so factoring we have m plus and m minus 7 is equal to 0. And for m plus 7 is equal to 0, okay, we'll have that m is equal to negative 7. And for m minus 7 equals 0, okay, so we have that m is equal to 7. Okay, and so just looking at setting up our table. Okay, so we have with our backdrops. Okay, so you have for the essential pieces, Again, we have f of m. Again, we have for m squared minus 49. Now for the zeros, if I arrange, again, in ascending order, so you have negative and positive 7. Okay, and so upon establishing a table of intervals, okay, so for what we have for the intervals case, we have at the smallest end, you have those values of x less than negative 7. You have those values between but not including negative and positive 7. Then we have at the upper end, we have those values of m. I think I said x earlier, but we're working with the independent variable m. Okay, so for what we have in the setup case, so we have 3 subinterval sections. Okay, so for test values m, okay, so I have anything less than negative 7, I can go with negative 8. And anything between but not including negative and positive 7, okay, 0 is a possible choice. And for anything greater than 7, I can just go with the number 8. Okay, and again, just separating the rows and the columns. Again, so we have negative 8, 0, and 8 selected as input values to which I can apply for the function. Okay. And again, we have the function is f of m is equal to m squared minus 49. Okay, so we have f of negative 8. And for f of negative 8, okay, so m squared minus 49. So I'm looking at the square of negative 8 minus 49. And the square of a negative is going to be a positive. So we have 64 minus 49. So this will come out to a positive 15. And for f of 0, so m squared minus 49, we'll have 0 squared minus 49. 0 squared is 0, take away 49. And we have for that result, again, we have minus 49. And for f of 8, okay, a little bit of history to repeat. Okay, the square of 8 and the square of negative 8 are the same. Where we have 64, and once again, 64 minus 49. Okay, this comes out to a positive 15. Now for the sign of f of m, okay, so anything selected for m that is less than negative 7, the output is positive. Anything between but not including minus 7 and 7, the output is negative. So we're going to have that f of m is less than 0, and anything higher than 7 selected for the input, okay, the output is going to be positive. All right, so we started out with m squared is less than 49. And again, just having translated, okay, in terms of a comparison to zero inequality, okay, so this is where we have f of m is less than 0. So we have, for number 29, okay, we have for the solution, we'll be looking at what is going to lead up to f of m is less than 0. So if you notice for the sign of f of m, okay, we have f of m is less than 0, and this will occur for those values of m between but not including -7 and 7. And so that will be the solution in this case. All right. Now, for what we have in the case of problem 33, okay, now we have the layout, okay, whereupon we have the function in factored form, and the inequality is already in terms of comparison to 0. Okay. Okay. So in this case, right, so you have this statement, you have along the lines of f of x is greater than or equal to 0. And just looking at what we have now, okay, so for this trio of binomials, where the product is going to be greater than or equal to 0 in the inequality, if we set this up where we have the product is equal to 0, okay, so that's going to be possible if any one of these three factors is 0. So if x plus 4 is equal to 0, okay, so we have that x is equal to -4. If x minus 1 is equal to 0, okay, so we have that x is equal to 1. And if x minus 3 is equal to 0, okay, we're going to have that x is equal to 3. Okay, so we have in the setup, okay, now we have the f of x is equal to x plus 4 times the quantity of x minus 1 times the quantity of x minus 3. And for the zeros, okay, and it turns out that these are already arranged in increasing order. So you have -4 followed by 1 and also at 3. And just setting up what we have with the table of intervals. Okay. Okay. So you have at the lowest end case, you have those values of x less than -4. You have those values of x between but not including -4 and 1. And then we have followed by those values of x between but not including 1 and 3. And we have those values of x greater than 3 at the upper end. Okay. Again, we'll be looking at selecting test values. See if I can. And we have again the sign of f of x. Okay, so just creating table space. Okay, so for any test values, we can select, okay, so for anything less than -4, we'll go with -5. Anything between -4 and 1, we can go with 0. And then between 1 and 3, if I go with an integer, I can only go with 2. If I only have for anything greater than 3, we can go with the number 4. Now looking at the function values, okay, so for f of -5, f of 0, f of 2, and f of 4, and just going ahead and getting to the output. So for -5, if I plugged in -5 for x throughout, -5 plus 4, -5 minus 1, and -5 minus 3. Now the product is going to result as a -48. And for f of 0, we have like 4 times -1 is -4 times -3, which will come out to a positive 12. And for the input value up 2 for x, now the output f of 2, this will come out to a -6. And with the input at 4, we have the output f of 4 to come out to a positive 24. And for what we have in the case of the sign of f of x, okay, so anything less than -4 selected, the output is negative. So in this case, we're going to have the f of x is less than 0. Second section, we have a positive output, whereupon we have f of x is greater than 0. Next, we have a negative output, so we have that f of x is less than 0. And then we have at the end, okay, we have a positive output, so we have the f of x is greater than 0. Okay, and so we have with our inequality in number 33. Okay, so again we have x plus 4 times x minus 1 times x minus 3 is greater than or equal to 0. And again, to get to the solution, we will reference where f of x is greater than or equal to 0. Okay, so for the solution, okay, now f of x greater than or equal to 0 again will be in the same direction as f of x is greater than 0. So where f of x is greater than 0, we have the second and last interval sections. And so we'll be involving the limit values -4 and 1 from the second section, and from the last, we're looking at 3 and infinity. And for the enclosures, okay, now again, infinities are boundless, so you have a parenthesis around infinity. And since we have the equal to 0 part made possible by -4, 1, and 3, okay, those three numerical values are included in the solution. And so we're going to have brackets to contain these numbers. And so that'll be an interval solution of what we have in the case of this problem. All right, now there is There's one more part, okay, and we dealt with polynomial functions, but just going back to rational functions. Okay. Now for rational functions and inequalities, in terms of how these are going to work out. Now, unlike polynomial inequalities, there's going to be a fixation on zeros, like what will be in the domain as well as what will not be, or what will be excluded from the domain. Now, let's say if I have r of x is equal to x plus 4 all over x minus 3. Okay, so if I were to, if you notice, you have a couple of x expressions, one in the numerator and the other in the denominator. So if I have like x plus 4 is equal to 0, I have x equal to negative 4. For x minus 3 is equal to 0, I'm going to have that x is equal to 3. Okay, and now just some things to mention in case you have r of x equal to x plus 4 over x minus 3. And now we have for the zeros, okay, so you got negative 4 and negative 4. Okay, this comes from x plus 4, which is in the numerator, and I can have a 0 numerator as long as I do not have a 0 denominator. Okay, now with x equal to 3, now that value creates a 0 denominator, but I'm still going to include this in the process. Okay, but now 3, okay, this one is not in the domain. Okay, so if the 0 is in the domain, okay, that value in x sets the function equal to 0, but like in the case of 3 not being in the domain, instead of setting the rational function equal to 0, it becomes an undefined expression. Okay, now for the interval portions, okay, so we have the lesser of the two zeros, you have negative 4. So those values of x less than negative 4. You have those values of x greater than negative 4 and less than 3. And we have those values of x, okay, greater than 3. Okay, and just like the polynomial inequalities, okay, now okay, so I can still supply a test value x. Okay, so anything less than negative 4, we'll say negative 5. Between negative 4 and 3, we can go with 0. Anything greater than 3, we can go with the number 4. Again, we have our function. Once again, we have r of x is equal to x plus 4 over x minus 3 So for r of negative 5, okay, so I plug in negative 5 for x. Negative 5 plus 4 is negative 1. Negative 5 minus 3 is negative 8. And a negative over a negative becomes a positive. So we have a positive 1/8. And for r of 0, okay, 0 plus 4 is 4. 0 minus 3 is negative 3. So r of 0, this will come out to negative 4/3. And for r of 4, okay, so you got 4 plus 4 is 8. 4 minus 3 is 1. And 8 over 1 comes out to positive 8. And for the sign of r of x, okay, so first interval we have a positive, where we have the r of x is greater than 0. Next we have a negative output. So you have r of x is less than 0, and then for the last we have a positive, whereupon we have the r of x, okay, is greater than 0. Okay, now let's say if we're looking at solving for the inequalities, okay, and say we have first of all, okay, so if I have x plus 4 over x minus 3 is less than 0, and I have x plus 4 over x minus 3 is less than or equal to 0. And if I have x plus 4 over x minus 3 to be greater than 0, and x plus 4 over x minus 3 to be greater than or equal to 0. And until I just kind of provide a bit of a segue. Okay, so we have for x plus 4 over x minus 3 is greater than 0, so we're looking at where r of x is less than 0. And we have in the case of the solution where r of x, x plus 4 over x minus 3 is less than 0, or r of x is less than 0, we have between negative 4 and 3. Okay. And now if I just jump to the greater than 0 part, here we have the r of x is greater than 0. Okay, so greater than 0, so you have for values of x less than negative 4, and also for values of x greater than 3. Okay. Now for the statements that include the equal to portion, where we have the r of x is less than or equal to 0. Now in the solution, you're still involving the limit values of -4 and 3. Okay, and let me do a little bit of underlining. Okay, if you notice, okay, we have -4. That part is in the domain, whereas 3 is not in the domain. And in terms of what we're going to have for the final phase, okay, so -4 is in the domain. Any 0 that is in the domain is going to create the equal to 0 part. So -4 is going to be in the bracket. 3, however, is a 0 that is not in the domain, and so that cannot create the equal to 0 part because it instead creates an undefined value. So 3, because it is not in the domain, that is going to be in the parenthesis. And we have with the final inequality, so you have with r of x greater than or equal to 0. So yeah, for the solution, so you're still involving -infinity, -4. Again, -4 is in the domain. So that is going to be bracketed. Again, 3 is not in the domain. So that's going to be in the parenthesis. Okay, and so those would be your outcomes. Okay, so for less than 0 and greater than 0, it can just pull from the top rows, okay, that are relative to what is involved. But for the equal to 0 portions, okay, you're looking at bracketing those zeros that are in the domain, but leaving in parentheses those zeros that are not. Okay, so you're going to have your respective solutions for this ratio with respect to 0, less than or equal to, greater than or equal to.